In this video we're going to look at solving differential equations using the exact differential form. So the total derivative can be written in this form here, du equals partial u by partial x dx plus partial u partial y dy. If you're unsure where that comes from, there's a derivation, a geometric derivation of it in the snippet section, so I suggest you go and have a look at that if you're unsure. Now if we set u of xy equal to 0, so it's effect we're taking a slice of a surface of some 3D object, then we can say then that the du is equal to 0. Now here's a little example of this here, and it gives us a motivation for what we're going to do next. So if we had a function u equals x plus x squared y cubed equals 0, then we can form the total derivative of that just using the equation above. So we've got to differentiate it with respect to x and multiply it by dx, and then differentiate it with respect to y and multiply it by dy. And I've done just exactly that there, and then we're going to set it equal to 0. Now that allows us to transpose these equations, so we can get dy by dx equals minus 1 plus 2x y cubed upon 3x squared y, and I've just replaced dy by dx by the y derivative, and then we can integrate that in order to solve it. So that's a motivation, but what we're going to do is we're going to do that, but we can work backwards, okay, in order to find the solution using an integration by the exact differential form. So let's say we had a function that's here. We have function m of xy dx plus a function n xy dy equals 0. In this instance here, the m of xy and the n of xy will be given by partial u by partial x and partial u by partial y. Now what we're going to do is we're going to test this and see if it's in fact an exact or total differential form. So in order to do that, we can we can see that the m is equal to the partial u by partial x and the n is partial u by partial y. So if we were to differentiate m with respect to y, then we would form the mixed derivative partial squared u by partial x partial y. And again, if we were to differentiate n this time with respect to x, then we would form the mixed derivative partial squared u by partial y partial x. And if the function is continuous, which we're allowed to assume, then these second derivatives, the mixed derivatives, will be equal to one another. So if these two derivatives are equal to one another, then this partial n by partial y must equal partial n by partial x. Okay, so this is our little test to see if we have our equation in exact differential form. Now, if that is the case, then we can see that we can find our value of u using two different routes. We could either integrate this m here with respect to dx, or integrate the n with respect to dy, whichever one turns out to be the easiest. So we would end up with u is the integral of m dx plus some constant that would be given by k of y, and u equals integral n dy plus some constant L of x. So either one of these would do. So let's see this as done in an actual example. So if we had the differential equation here, and we're going to try and find the solution of this u as a function of x and y, then what we're going to do is test first of all and see whether it's an exact or total differential. So what we can notice is that m is equal to the first term and n is equal to this second term here. So then what we can do is we can differentiate m with respect to y, which in case we get 6xy, differentiate n with respect to x, and we get 6xy. So both of these are equal. Both these are equal, then partial n m by partial y equals partial n by partial x. So it is exact differential form. So now we'll go through and we'll look at the solution. So what we could do is we can then use either one of these in order to form the solution. So we can use either this one here or this one here to form the solution. So in this instance here, we've decided we're going to look at u as the integral of m dx plus ky. So that's just going to be the integral of the m section here. So the m is this here. So we integrate this plus kxy, we get the value u below. So that's our solution there, but we don't know the value of kx and y, k of y, but we can find it is what we can do is we know that if we differentiate du by dy, then we know that the du by dy is going to equal our value of n, okay? And we can see that when we headed up here, because our du by dy will give us our value of n. Okay, so we just differentiating above here with respect to our dy, and that will give us our 3x squared y. So just differentiate that with respect to y. So we get 3x squared y plus, when we differentiate k of y, we get dk by dy, and that equals our value of n. But we already know our n equals 3x squared y plus y cubed. Okay, so, and we got that there from our original equation. That's our 3x squared y plus y cubed. Okay, so now we know we can equate the values in each of these. We've got this here is equal to that, so the dk by dy equals y cubed, so it means that dk by dy is y cubed, so we can then integrate this and get that k equals y to the 4 upon 4 plus some constant c. So then we can take this and we can put this back into our original equation up here for the k of y. Now whenever we do that, we have this, our differentiated solution, and we've added in our y of 4 upon 4 plus c. So then we can take out the common factors here and just take c over the other side, and we can make it a positive because it's just a constant, so we can do what we want with it. So this is the final solution here. Okay, so that's a quick description of one example using the exact differential form. Okay, thank you for listening and goodbye.